theorem for the deflection of beams. So we have the problem one. Let's go. This one is your problem one. That you got a fixed beam subjected to UDL for the entire span of length L. Get the value of delta maximum, that is delta at mid. So if you use the superposition theorem, that we have one more compatibility. We have compatibility condition. If you use the compatibility condition that theta at the ends is 0, if theta at the end is 0, that means there should be because of the external loads. Let's treat it as a UDL, so it gets deflected by some amount of theta, that equals to, we know that the result for that is WL to the power 3 WL to the power 3 by 24 EI. Is it so? Yeah. So there should be some moment developed at the end spans that we call as fixed end moments. There should be some value of moment, fixed end moment, such that it resists this change, so that theta net becomes 0. So we have that for this beam, we have fixed end moment. Then we calculate that, and we have the diagram for the final moment diagram is looks like this one. That this one is your WL square by 12 and WL square by 12 for the beam subjected to a uniformly distributed load. This one is your variation. So we have to make this theta 0. So there should be some anti-clockwise moment acting at the end span. Let's say this was your simply support beam. There should be some anti-clockwise moment of M applied at the ends, such that the theta here is acting, theta developed here is anti-clockwise, theta 2, here it was theta 1, it was clockwise. So we can have that theta 2. We know that if you have a simply support beam, you apply moment on one of the supports, then the theta here, theta near, equals to ML by 3 EI, and theta 4 equals to ML by 6 EI. Similarly, if you have simply support beam and moment is applied on one of the supports, so we have that theta near is ML by 3 EI, and here theta 4 is ML by 6 EI. If you add the two, you can get the effect of this one. So when you get the value here, we can get theta 1 plus theta 2, that is ML by 3 EI plus ML by 6 EI. Finally, you get value of ML by 2 EI. ML by 2 EI. If you equate that, theta 2 should be equals to theta 1. You can equate them such that the delta at the end is equals to 0. So theta 2 equals to theta 1. We have theta 2 equals to theta 1. So your theta 2 we know that equals to M L by 2 EI, and we equate it with WL to the power 3 by 24 EI, and we can get the value of moment developed at the ends that we call as fixed end moment. So fixed end moment developed equals to WL square by 12. That I already showed you here. WL square by 12. So we can get the now we can get the value of delta at mid. Let's say it deflects by an amount of, let's say simply support beam deflects by an amount of delta 1. We know that delta 1 for simply support beam, that equals to W 5 by 384 WL to the power 4 by EI, and you have one more beam because of the moments developed, fixed end moments developed. The delta here would be some delta that we have results that delta at the mid is equals to WL square, that moment ML square by, I think 48, ML square by 8 EI. This is an important result also. You can remember, you can keep it in your notebook, that ML square by 8 EI. That is upwards. This one was your downwards, and this one is your upwards, delta 2. ml square by ATI, and equate them. Then we can write delta final at the mid, that equals to 5 by 384 WL to the power 4 by EI. Then minus, we can write that minus m value was WL square by 12 and your L square by ATI. So we can get the value that 12 into 8 inverse minus 5 by 384. That's 1 by 384. 1 by 384. That's 1 by 384 WL to the power 4 by EI. Delta net, delta mid, or delta maximum. So final diagram say this one. Here theta here is 0 and delta here is 0 also. So we get some deflection. So this is your delta maximum. And if you say this is 1 by 384, and for the simply support we have 5 by 384. This one is your 1 by 5th of this one, simply support beam. Now going further for your superposition method, say that if you want to make the that bending moment diagram for this, say here this was WL square by 12. If you want to make the shear force diagram, because of the loading here the shear force would be WL by 2. So the shear force of WL by 2, and here it would be also WL by 2. Then you join the two, so it cuts here at the mid span. If you want to say what is the value of this loading shear force diagram up to the point at mid, we can write half of WL by 2 into L by 2. That's WL square by 8. So when you say what is the value of bending moment here, we can write WL square by that area of the triangle, WL square by 8 minus of WL square by 12. That's moment at mid. That's 8 inverse and plus 12 inverse. That's, yeah, we know that moment 2 minus moment 1 equals to VDX, shear force area. Shear force area is positive, so this is your positive value, shear force value area. Then we have m2 minus m1. Moment 2 is your negative, so moment 2 is your negative. That means negative of negative. Then you transfer it, it becomes negative. Final it becomes negative. So you have to subtract it. So you got value of WL square by 24. We got WL square by 24. This is your WL square by 24. This one is your 12. This one is your 24. That means moment at this end is more. Moment at end is more. Moment at mid. Moment at end is greater than moment at mid by an amount of 2 times. We can say moment at end equals to twice moment at mid. So if you want to say why it cuts the section, say this is your point of counterflexure. To calculate the point of counterflexure, we can write that you got a fixed end moment of WL square by 12, and you had a shear force of WL by 2, and you got a UDL of W into X. So you have shear here, the moment here is mx, that's also 0. So we can write summation of moments at x equals to 0. Then we can write WL square by 12 and minus the plus this one is a negative, then plus WL by 2 into x, then minus WX square by 2 equals to 0. We can get the value of x equals to that. We get two values because structure is symmetric, so your deflection profile is symmetric and bending moment diagram is symmetric. So your delta, two values of 2 point of counterflexure. 2 point of counterflexion where values are at x equals to 0.211 L and 0.788 L. Now we have few more problems on your superposition method. Let's go for them. Let's say this was your beam and you got this is cantilever. You apply a load of P here. There is a spring attached. Downward at the downside, but fixed at the bottom. So we have to get the you have to get the value of that, get the value of Fs, force in the spring. Let's say spring has stiffness of K. We know that F equals to K delta. So we can have the compatibility. What should be the compatibility condition here? That let's say the spring was not there. You apply load P, it would get deflected downwards by PL cubed by 3EI. But because of the spring, and here it is fixed, so final structure won't go downwards by any amount. Let's say if this goes downwards by this amount, the spring has to get compressed by same amount such that A and B are relatively at the same position. That means delta relative of A and B should be 0. There should be no relative displacement between A and B. There should be no relative displacement between A and B. So for that we can write that deflection in as beam AB, deflection in beam, that equals to compression in spring. Compression in spring. If we write that, we can conclude that let's say the reaction provided by the spring is force Fs. So we can make the free body diagram. Say this was your load P. Say the reaction here is upwards, such that there is compressive force in the spring. Say this is your spring. In that there is compressive force of Fs. So we can write that P minus Fs L cube by 3EI, PL cube by 3EI, PL cube by 3EI. Then equals, this should be equals to Fs by K. Then you calculate the value of Fs from this result. Then say we have one more problem about the same concept. So this is your bar AB and this is your bar CD. You have attached it as spring. Now let's say you apply a load also P. You apply the load P. We can say that AB would deflect by an amount of some amount delta. Let's make the free body diagram. Say here the force is P, and say that the spring provides a force of Fs, and same force would be compressive in the spring Fs, and here the spring same force upwards Fs, and same force would be transferred to the this beam CD. This is the free body diagrams of the entire structure, and we can say that beam, we know that beam is also as spring. We can treat beam also as spring, as we have that standard result, that PL cube by 3EI, PL cube by 3EI, that is delta. If you multiply delta with stiffness sum K of the beam, you can get the force value P. So your K beam becomes equals to 3EI upon L cube. 3EI upon L cube. So this is just stiffness of the beam. So we can say that the beam is acting. Beam is say this is your beam. So we can treat beam as a spring. So since for the series connection, we can say that spring and beam AB and beam CD this beam CD and your spring are in series, because your force is same in both the members. If force is same between two members, that means they are in the series. Let's say this, that you have this one and you have this one, then you attach the mass M. We can say mass is acting force of mg downwards, here mg. Then in the spring one there is downward mg, here downward upward mg. Similarly in this one, downward mg, upward mg. So force is same in all springs because they are in series. when the springs are in series, that then equivalent, then k equivalent becomes equals to 1 by k1, where that 1 by k equivalent equals 1 by k1 plus 1 by k2. Then we get the value of k equivalent. So we also can say that, let's say that AB gets deflected by amount of delta, and say CD gets deflected by amount of delta. This was your delta 1, this is your delta 3, and say spring also gets, because spring is elastic, so let's say spring also gets deflected by an amount of delta 2. We can get the relation between delta 1, delta 2, and delta 3. Before that, let's make the same problem in this fashion. Say this was your member AB, and this was your CD. Then we can assume that bar is rigid between the two beams. If this is we can say it is a rigid bar. For rigid bar, there is no deformation, so it can't go compression. Rigid bar itself can't go compression. There is no negative or positive, say no compression or extension, no compression or elongation. Okay, say this is equals to 0. So for the rigid bar, say now if you apply load of P, AB gets the downwards by some amount of delta. Since the bar itself, since the rigid bar can't go compressed or elongated, it would itself go downwards by same amount of delta, such that the final configuration would look like this one. So your delta, so we can write delta 1 equals to delta 3. Then delta 1 equals to delta 3. So in this manner, we can say that your delta 1 has to be equals to the compression in your spring, so that delta 2 plus your deflection of beam CD. So that means that deflection in CD is only amount of how much AB gets deflected and how much spring gets compressed, That's how much CD was going to go downwards. So it's let's say AB reached to this point. This was your point B. Then after that, spring also gets compressed by some amount of, say actually the spring should have been reached to the point. So the spring should have been reached to the point here, but it's getting compressed by this amount. So spring finally reaches to this point. So from that there was D. So it D has to go only this part. So we can write delta 1 plus delta 2. Delta 1 equals delta 2 plus delta 3. And from the free body diagram, we can write what's the value of delta 1. We have the value of delta 1 equals to Fp minus Fs L cube by 3EI, this one. And after that, this should be equals to your force in spring, Fs by K, plus your deformation in the bar CD. For the bar CD, you have force of Fs. This is the force of Fs. We can write that Fs L cube by 3EI. So you can get the value of Fs after calculation, that Fs equals to 0.25 of P. That's 25% of P. Also, we can solve it by that equivalent spring concept. That the equivalent spring between that bar CD and your spring, we can get the equivalent spring between the two. So let's say that the spring constant was, say 3EI by 2L cube. So if you substitute here, say this was your spring Ks and this was your K bar BD. So we can write 1 by Ks was your 1 by 3EI by 2L cube plus spring of the stiffness of the beam. Stiffness of the beam is, we know that stiffness of the beam subjected to point load at the end span, that is equals to 3EI upon L cube. So we can get the K equivalent. K equivalent comes out to be equals to EI by L cube. Once you got the K equivalent, we can treat that as a single spring. Say this was your bar AB, subject to point load P, and your spring is also there. So this is your K equivalent. Now the bars, we can say, if you cut the if you make the free body diagram, say here the force is P. This is similar to the case we solved the first question of these springs. So this is your P. Here the spring force constant. Say the spring force is Fs, and here the spring force is Fs, and we have that relation that that delta elongation in the beam should be delta compression in the spring. So this is your compatibility, that if delta is same, that means springs are in parallel. So we can solve by that method also. If springs are in parallel, we can have K equivalent equals to summation of Ki. That means K1 plus K2. So your first one is your 3ei upon L cube plus your K equivalent was ei upon L cube. So our final value is 4ei upon L cube equals to K equivalent 4ei upon L cube. And for that we also had that delta is same. For delta is same, that means we can write Fp minus Fs L cube by 3ei should be equals to delta in the spring. What should be the delta in the spring, whose stiffness is of K equivalent? So we can write Fs by K equivalent. Your value of K equivalent was ei upon L cube. Fs by ei upon L cube. So we can get the value of Fs equals to 0.25 P. So in the both methods, you can get the value of P equals to that force in the spring is 25% of that force in the that bar. Force that 25% of that load P. Now we have two more problems on the superposition method. Then we will end up this this lecture. Let's say that you have beam, simply support beam of 2 meter, and a load is acting at the midspan, and you have connected a spring. Then after that you have one more beam of one more beam of total length of 1 meter, such that this is 0.5 meter, this is 0.5 meter, and you need to get the values that you need to get the value of K equivalent, and you need to get the value of force in spring. You need to get the value of force in spring and K equivalent. Let's say the force let's say the stiffness in the spring is, let's say that the spring Ks, let's say that Ks equals to 1 and Ei equals to, let's say spring Ks is 48, Ei is equals to 1. The units doesn't matter, because we would be dealing in the units. We would see how the units don't affect our relation here. Let's say the Ks is 48, Ei is 1. We need to get the value of K equivalent and value of Fs. So for K equivalent, there should be that is either in series. The springs should be either in series or in parallel. We want to see whether they are in series or in parallel. So we want to make the free body diagrams. Let's say that the spring is opposing the load P, such that the free body diagram for the first beam looks like that P, and here is some force P, Fs. Then say the final deflection would be somewhat this one. We know that the result for simply support beam subjected to point load at the midspan, we write that P minus Fs. So this is your load, net load. We write P L cube by 48 Ei. And if you substitute the values of L is your 2 meter, A, B, C, D. This is your AB. So for the AB, your length is 2 meter. We can write 2 cube by 48, and value of EI we can write 1. So finally we get P minus Fs divided by 6. 2 to the 4 to the 8, 6. So delta 1. Similarly, if you want to make a free body diagram for the spring, there will be some compressive force on the spring, Fs. So your delta in the spring, we can write delta in the spring would be compressive delta deformation, that's equals to Fs by delta, Fs by k, Fs by k, k is your k spring, that means Fs by 48, Fs by 48. And similarly, same force will be transferred to the beam CD. This is your beam CD. Your force of Fs is transferred at the midspan of the beam. So say the delta is here, delta 3, that is equals to Fs. Your length is 1 meter cube, 1 cube by 48 into EI, that means Fs by 48. And from the compatibility, that say we can write delta 1 is, so this one is your delta 1, this delta 1 has to be equals to deformation, compression in the spring, and deformation in the bar 2. So let's say it gets deflected by amount of delta 1. So spring has to go compressed by some delta spring, and after that the net which remained same amount has to be shifted. This bar has to go down by that amount. So we're at that compatibility condition. And when you substitute the values, the three values here, we can write the value here was P minus Fs and L cube by 48 EI. This was equals to Fs by delta, Fs by k, Fs by k, k was 48. Similarly, plus delta 2 was your Fs 1 cube by 48 EI. So when you substitute here, we get a value of Fs equals to 0.8 of load P. So we need to get that Fs equivalent. So for the equivalent, k equivalent, we can write that we can see whether the bars are in series or in parallel. See, for the, so when we make the free body diagram, we said the net force in the bar AB is P minus Fs. Then after that, in the spring there was a net force of Fs, okay, Fs, and same force was transferred to the beam CD. That means spring and CD are in series because force is same. If both are in series, we can add the two. Let's say we can write k equivalent, that equals to k spring and k bar into k bar plus k spring equivalent, k1 k2, k1 plus k2. K spring was your 48 and k bar, that was k bar is your 48 EI upon L cube. Say for this beam, say it deflects by amount of delta. We know that delta equals to PL cube by 48 EI. If you equate with P by K of the bar, you can get value of K bar equals to 48 EI upon L cube into 48 EI upon L cube. L cube is your length of 1 meter. This is 1 meter length. 1 cube divided by 48 plus 48. Finally, you get 48 plus 48. That equals to 24. You get a k equivalent of 24. So now you can make the diagram look like this one. This is your k equivalent. Now you have a load of P here. So we can say, similarly we can say that force, that bar AB and S and spring, equivalent spring in parallel. If they are in parallel, you have to add the two. K equivalent equals to the stiffness of the bar AB, that's 48 EI upon L cube. The value of L is here 2 cube, then 2 cube plus your equivalent of 24. So you can get the value of 30. K equivalent is 30.